free to chime in at any point, and I'll stop after each question as well, just to make sure. Okay, so we'll be going over the 2019 test 2, which is in the course resources drive on Avenue. So we'll start with each question and go through, and just as a disclaimer, I'm also in this class right now. I do not know everything. I'm just simply here to give any information that I can. Okay, so question 1, the first part is just asked to calculate the velocity, momentum, and wave number for an electron with a specified Fermi energy. We'll start with that. So we know that the energy is equal to this equation here. So if we want the velocity for part I, we rearrange that, it'll be square root of 2 EF over m, all under that square root. And so this EF, we're given in the question to be 5.5 electron volts, which we're going to convert into joules to use in the equation. This gives us an energy of 8.8 times 10 to the minus 19 joules. And we know the mass of an electron is given to us in like the first page typically of the test. And so plugging all those back in, I'm not going to write the numbers in just to save time, but I just plug in the E here and the M equal to your 9.11 times 10 to the minus 31 kilograms. So plugging that in, we have a velocity of 1.39 times 10 to the 6 meters per second. And then part 2 is asking for the momentum, which we know is just equal to the mass times the velocity. So we take the velocity that we calculated in part 1 as well as the mass, plug it back into this equation. Again, I'm not going to write it out just to save some time because we gotta go through the entire test. We have 1.267 times 10 to the minus 24 kilograms meters per second. And then part 3 is that wave number K, as well as the wavelength. So first, we know that K is equal to 2MEF over H. So plugging back in the mass as well as this energy here with the H value, which is also given as a constant, we get K to be equal to 1.2 times 10 to the 10 meters to the -1. And then wavelength, simple relationship of 2 pi over K is equal to that. So plugging in the K from above, we get a wavelength of 5.236 10 to the -10 meters. So part A was pretty simple, just plugging in some equations. And then the next part for part B is asking specifically at what temperature we can expect this 10% probability that electrons will have it. And then this energy is 1% above the Fermi energy that we were given from above. Okay, so we know that it's that 1%, so 5.5 electron volts times the 1% gives us a small number of 0.055 electron volts, and then converting this again to joules. We get an energy of 8.812 times 10 to the minus 21 joules, so smaller than before. And we also know that the energy is going to be equal to this energy plus this energy here. plus its original. So E plus EF, which means that this E minus EF term will be equal to the calculated value. And that is going to be handy in the Fermi energy equation that we see here. Oops, that's of energy. And this gives the relationship between the energy and the temperature, which is what we're asked to find. Sorry. So we plug in this term here, this number to this part there, and then we know everything else from before. And we're going to basically rearrange to solve for this temperature, knowing that this Fermi energy here is going to be the 10% probability from the question. So this, like this side here, will be 0.1. There, and then we basically rearrange this just to solve for temperature. Once we have that, temperature is 290.41 Kelvin, because this K here, right here, that's just the Boltzmann constant that we also know from above. And so that's the final answer for B. And then we look at part C, which is more of a discussion question. It's just asking to discuss the motion of Fermi electrons in the periodic lattice and with an emphasis on the other factors. So some things to mention in this type of like explanation questions. I'm just going to kind of point out some like key factors. There's obviously a lot of other things you could talk about. So electrons here obey the Pauli exclusion principle. Oops. As well as the electrons undergo Bragg's scattering at these Brillouin zone boundaries. Oops. I always spell this word wrong. In zone boundaries. And that's proportional to this. We also have this equation to describe them. And notably here, this p-value. When this p-value is large, there's more narrow energy bands. And then when it's smaller, we have wider energy bands. Another thing to mention is just like the overlapping of the atomic orbitals that give rise to the energy bands. So just some like points you can mention to kind of explain this one, as well as there's other things that you can talk about, more of like a text answer compared to all the other ones. Did you have any questions about anything that we went over in part one? Okay. Perfect. And we'll move on to question number 2. So this one is talking about a high purity metal with a given amount of free electrons per centimeters cube, as well as a conductivity, and then the size of the wire. And so then we're asked to calculate a whole bunch of things here. So we'll start off with part A of this question. So 2A is asking for, oh, screen froze, the resistance of this wire specifically at room temperature. So we were given the conductivity up here, and the resistivity, defined as P, is just 1 over the conductivity. An equation that we can use to find the resistance of the wire itself is just this one here, PL over area. So we're given the diameter and the length, so we can plug all of these in to find our resistance, which will basically be 1 over the given conductivity to find the resistivity. Length of the wire is 1 meter over the area, which is just pi times the radius. I'm just leaving this stuff all in meters to make it simple. And then solving for the resistance. We have 0.0215 ohms. And then the second question is part B of this is asking if the wire is given a specific amount of current, what is the voltage and the electric field's strength that is developed within the wire under that applied current. So we know from our Ohm's law relationship that the voltage is just equal to the current times the resistance. You can plug in the 1.3 amps given in the question up here, as well as the resistance that we calculated in part A. And we have 0.028 volts. And we also know this electric field strength is just the volts over the length, which in this case, we have this many volts, and the length of the wire is just 1 meter. So we're left with the same number, just with the units of volts per meter. Okay, and then part C is asking for the relaxation time of electrons between collisions, and you're also given this formula up here, which we will use. So here we're given that this relaxation time equal to this formula. However, we don't have all of those values, but we do have this relationship as well, so that we can replace the VF in terms of things that we already know and are given in the question. So if we take this here and we're going to plug it back in there in this equation for the relaxation time, and we can cancel those terms, and we're left with a formula in total of mass conductivity over this electron charge, as well as the number of electrons in that given amount of volume, which we were given at the top here, this 8.5 that I've already highlighted in green, that number there. So taking those, we can plug in and solve for the relaxation time. And just to make sure to convert this number here into meters. So solving this, we are given a time of 2.472, 10 so minus 15 seconds, so very small. And then in part D, it's asking us to calculate the mean free path of electron between collisions. They also gave us a formula for this. So we know that this formula has to be here. And we know from above that this VF term can also just be rewritten like this in terms of everything we know. So we plug that back in. So using our relaxation time, and then we've already basically found all of these parameters above as well. We've used them. We have an answer of 3.009, the weird units of SS per meters coulomb. And then part E, this was a test that we have from 2019. The solutions that were given were not correct. However, that is exactly how I would have solved the problem. So I am not sure how he wanted it because the student did not receive full marks on those solutions. Be something I would recommend asking the professor. So we'll skip over E, but in terms of F, this is another one of the kind of like not calculation, but more just general knowledge ones. So this one's talking about like the main assumption correction about the density of conductive electrons used in the derivation of conductivity in quantum mechanical theory. I didn't really know much about this one before, but there is a lot of good information in the textbook too, if you're curious about it. So the main thing is that these free electrons are assumed to be conductive in classical theory. In that in quantum mechanics, they're only assumed to be conductive only when their velocities are like close to um, their Fermi velocities. And so it's just because they're most dense closest to that Fermi energy. And the increase in energy will make them more conductive due to this density. Okay. And do you have any questions about question 2? I know I didn't have a good answer for E's because I simply don't know how else to do the question. Perfect. Okay, so moving on to question number 3. This is kind of split up into a couple different parts. So we'll just start with number 1, where it's asking for the effective mass if the electron is first moving in a vacuum and then in a conduction band, given this relationship here. And notably as well, we know that this here, m star, just means effective mass. So for part A, we know that we're going to have to basically find this relationship of the energy to plug it back in to get the effective mass. So we know that for something, an electron that's like given in a vacuum, this energy is going to be given by this equation here, where MO, I'm just gonna write it up here, is rest mass. So if we take the first derivative of this with respect to K, the 2's will cancel. Oh, that's K squared in this equation. And this one here is just K, and then that 2 cancels out over MO. And then the second derivative of this energy with respect to K will just be equal to this squared over the rest mass. And then if we plug it back into this equation here for an effective mass, we know that it'll just be equal to this. And then essentially these cancel out, and we have that the effective mass will be equal to the rest mass for an electron that's specifically in a vacuum, which means that this mass is just the 9.1 times 10 to the minus 31 kilograms. So the same as its rest. Now for part B, it's the same thing, but now we're given a different relationship of energy. Notably also here, this H is not the one with like the cross through it, so it is defined differently. So taking the first derivative of this with respect to K, we're given this relationship, and then take the second one so we can plug it back into that equation. We have 2H squared over 1.4 rest mass. So now we know that our effective mass is going to be equal to H over this expression we just derived. And we don't have a cancellation like we did up top. So once we plug these values in, knowing that both of these are just constants, and then your MO was just defined as the 9.1, we get an effective mass here of 1.618 times 10 to the minus 32 kilograms. Okay, so that was just part 1 of question 3. And now part 2 is asking for the numerical value of the curvature, and we can also notice here that we're given an equation as well for curvature of the above dispersion relationship with that, again, relationship of energy that we saw in part B. So from above, we know that the second derivative, so use it again in the curvature equation, is equal to 2h squared over 1.4 MO. And this curvature is simply just equal to that second derivative of its energy. And plugging those numbers in again, we get 6.89 times 10 to the minus 37 joules squared second squared per kilogram. Okay, and then we have question 3, which is asking again for the effective mass of an electron obeying the dispersion relationship. So we already know that this is the value here. for the second derivative. So going back to the equation for part 3, that m star is equal to h for d. We're basically going to take this and plug it in as that number with the same h constant that we have seen before. To get an effective mass here, 1.618 times 10 to the minus 32 kilograms. And then question 4. We're given this information here. We can talk about again that same relationship as well as define energy and the mass. We're asked to calculate the velocity in part A and then the wave number and wavelength for part B. So for A, we're going to again use the given relationship, energy is equal to 1/2 mass velocity squared. Rearrange this for velocity. And then we're given the energy to be 100 millielectron volts. I was going to convert this to joules to be able to use it in our energy relationship. So plugging in this energy into here, as well as the mass of electron of 9.1 times 10 to the minus 31, we get a velocity 1.876 times 10 to the 5 meters per second. Then part B. So we know already that this energy here, h squared k squared over 1.4 times the rest mass. We rearrange this for k. And then just sub in these values once again, where h is that Planck's constant and k is that wave number. Then we get k equal to 2.16 10 to the 8 meters to the negative 1, and then use the same wavelength relationship that we've used earlier of the wavelength is just equal to 2 pi over k. And then we have a wavelength 2.914 times 10 to the minus 8 meters. So that's 4B. So we've done all of question 3 now as well. Do you have anything you want me to go over? Also, yes, Josh, this did start at 7. I just saw that message now. However, I did record it from the beginning, so I can make that available if you want to watch the beginning of it too. Okay, so if you guys don't have any other questions, we'll move on to question 4, and then we'll be done probably pretty early, so we'll be able to go over any questions you guys have too. Okay, so question 4 is all about Fermi energy levels again. So we're given just 2 diagrams of these Fermi levels and their work functions of 2 different metals. And then the first question is just to briefly discuss, notably with helps of graphs, what will happen if these 2 metals are brought together to form like a metal-metal junction. So for this, what's going to happen is essentially, I'm just going to write out just kind of like the jot notes of things to talk about. So essentially the Fermi levels are going to like equalize in like the middle. Not always exactly the middle, but they're going to kind of like equal out because the one metal will donate electrons to the other one. And then the voltage that's produced by this metal to metal contact is proportional to the values here. And I'll just kind of highlight that this is these relationships of the metals. So you bring them together, the voltage will just be the difference between the two. Excuse me. And then in terms of graphs, we first have, oops. For the first metal, and then the second one, which was taller. And basically when these are put together, you're gonna have this relationship over time where they make this difference in the middle. And this part right here is just your the one of the second metal minus the first, which is the same thing that we kind of talked about with the voltage produced in word terms already. That's kind of what's happening there. And then in terms of its energy, we will have Fermi energy relationship that will look like this, similar to what you've seen in the other ones. And then part B is asking for the relationship of the energy as a function of the density of state diagrams for the two metals before and after the contact. So for this, we'll start with the before ones. So before the two are separated, so we'll have one for metal 1 and one for metal 2. Not very good at drawing straight lines, apparently. Gosh, that's even worse. And then looking at these above, we know that metal 1 has a higher Fermi energy than metal 2 before. So just make sure that that's represented on the graphs. This in red. Then this one is a bit lower. And they still follow the same trend up. And then after they're brought into contact, their Fermi levels equalize and they have the same, like they're both had the same Fermi level, so we can represent it on one graph. And it'll kind of be in the middle of the other two from what they were before they were joined. So it'll be somewhere kind of in here. And that's what it'll look like. So now this is the metals once they're joined together and they both exhibit this Fermi energy amount. They're both the same. Okay, and part C is just to briefly discuss two different effects as well as their applications. So again, I'm just going to kind of write out like some main points to talk about. So the first one is the Seebeck method, or it's not method, but like effect. So this one is seen in thermocouples and is essentially when you have two different materials that are connected at two different junctions, which kind of forms like a loop. And then they're also placed in a temperature gradient. So one of these junctions will not have the same temperature as the other one. One will be a lot hotter. And this basically creates voltage. And then the second one is the Peltier effect. I don't know if I'm saying that right. So this one is used in refrigerators and other like cooling devices, essentially. How do you spell refrigerator? I actually don't know. Fridge. Ator? That's probably wrong. I'm sorry. And this is used when current is specifically run through kind of a similar setup where you have two different materials connected at two junctions to form that loop. And then one of these junctions will heat up. And then one cools down. And depending, like the dependence of which one heats and cools is dependent on the direction of the current. So you can change it as well. So those are everything for question 4. And we are done with quite a bit of time left. So if you guys have any questions or anything else you want me to go back over, if I went too fast over anything, let me know.
Yeah, I just had a quick question. Were you like about the class?
Okay, yeah, I'm currently in this class right now, so I won't know everything.
Yeah, I thought so. Were you there on Friday?
No.
Oh, okay. I was just wondering if you thought like like a bunch of this stuff from question 4, like we haven't really gone over.
Yeah, this could also just be like due to like the times you did it in. I kind of talked about I feel like I remember doing some of the Fermi stuff like coming about it when I was doing the labs.
Oh, right.
And I don't know like I'm trying to remember to test one if there was anything on there that was like more specifically taught in the labs and anything else. I feel like it wasn't.
Definitely not.
Um but I do know the course has been restructured since 2019. So we may not see something about these like Fermi energy levels. Um So I don't know like how relevant specifically it would be.
No, yeah, I was just going over like the test and some of the other practice
Mhm.
questions, and I was just really confused. I was like, yeah, we haven't gotten
Yeah,
to half of this.
there's a lot of really good information about it in the textbooks as well about the Fermi energy. It does a good job of explaining it from the beginning. If
Okay.
you do want to look at it, because that's what I looked at to kind of like understand this part. Because I remember stumbling across it when I was writing one of the labs. I don't remember which one it was now.
Yeah, is it in the course resources?
The textbook?
Yeah,
I'm not sure. I can double check, and if not, I can add it like right after this.
that would be great.
So I have the PDF version.
Did you also happen to do any of the tutorial for this one or?
I have not personally, no.
Okay,
I was planning on doing it this weekend, but I never got around to it.
that's all good. Yeah, because some of them are like really tricky.
Okay, yeah, no, I haven't done that one yet.
All right, I'm gonna head out then. Thank you.
Okay, no worries.
Thank you so much. Have a nice day.
You as well. Bye.